Hi, good afternoon, everyone. I'll keep this a bit short and engaging because everyone looks tired. So, so my name is Niham. I'm currently a final year undergraduate at IIT Madras, India, and I'm here to present my talk on counterfactual explanations for visual recommender systems. So let's motivate our problem statement with a user with an example. So let's say we have Jane, who's an active user at fashion.com, and like looking at the recommendations, she wonders why a particular dress was recommended to her. So there's a growing need to ensure that users understand and trust the system. So let's go over our problem statement. So we want to provide counterfactual explanations for the recommendations provided by the recommender systems that make use of visual data for their decisions. So yeah, that's a lot of jargon. So let's break it down. So what are visual recommendation systems? So visual recommended systems are a particular type of recommender systems that uses visual content such as images to provide personalized recommendations to users. So this is very useful in fashion based scenarios. So let's say the user has bought a particular type of fashion items previously. So like he'll buy similar sort of items in the future. So this basically utilizes pre-trained deep CNN features which have been like trained on a classification data set such as ImageNet. So existing explanation strategies for these type of systems, they focus on correlations in item features and user interests. But what they lack is that they like these type of explanations might not find the causally important features. So to find the causally important features, we provide counterfactual explanations. So let's motivate counterfactual explanations by an example. So like counterfactual explanations reveal what should have been different in an instance in order to observe a different outcome. So we motivate this by a loan application example. Let's say we have a user and he applies for a loan, but he gets rejected. So a simple explanation would be that salary was one of the motivating factors why your loan application was rejected. But the main advantage of a counterfactual explanation is that the counterfactual explanation says that if your salary had been 40,000 instead of 30,000, your loan request would have been approved. So it reveals what should have been different in order to observe a different outcome. So the prediction is getting changed and the model is saying what should have been different. So the main advantages of counterfactual explanations is that it's more understandable and it provides a causal understanding of the aspects which lead to the recommendation. So in our problem setting, these explanations are concise, scrutable, and actionable, as these are minimal sets. And another advantage is that they do not expose any information about other users, and so it doesn't have any privacy concerns. So yeah, so this is why we should have counterfactual explanations, because they provide more control over the system. The providers can debug the system better, and it's better than associative signals. So I'll go over our method in brief. So CAVIAR, or counterfactual explanations for visual recommender systems, extracts the visual features most relevant for the recommendation by finding the least perturbation to the item's image embedding. So the item image embedding is basically what we obtain using a pre-trained deep CNN model. So let's say it's like AlexNet, which has been pre-trained on ImageNet. So we get the item image embedding using that, and we perturb it. So we add a delta vector to the item image embedding such that it is displaced from the top K recommended list. And to do that, we minimize this delta in such a way that we perform a search in the image feature space and return the optimal counterfactual image features. So I'll give an example of the explanation. So let's say we have a user A and item ID and an item image. So the counterfactual explanation in this scenario would be, if the item had the color black instead of white, it would not have been recommended. And let's say we have another example where the t-shirt is of short sleeves. So an explanation given by our model is that if the item had long sleeves instead of having short sleeves, it would not have been recommended. So this type of scenario is like has applications in interactive recommender systems, which allows users to feel more in control of the decision-making process. It increases the transparency and fairness. By providing an alternate recommendation, users can make a more informed decision, and they can obtain a degree of personalization that they desire. So I'll go over the base recommender system that we use in our method. So our method is quite general and can be applied to any system that uses image-based embeddings. For this work, we use a modified version of the visual Bayesian personalization ranking paper. So we replace the pre-trained image features, like they use AlexNet, but we use the pre-trained image encoder of Clip. Now I'll hand it over to my co-author Vibhu for the rest of the talk.
Okay. Thanks a lot. I'll take you over the remaining slides. So this is a broad overview of our entire system. Towards the left, you can see the base recommender system that we use, which Neham just explained. And towards the right, you'll see what our actual explanation model is. It looks like a lot. I'll be coming to a slide that has only that in it, and I'll explain it step by step. But yeah, basically that's the explanation model. So, yeah, so what is Clip? So Neham has been saying that we've replaced AlexNet with Clip. So what is Clip? So Clip is basically a multimodal model that combines the knowledge of English language concepts with semantic knowledge of images and allows us to connect visual features in an image with natural language text that describes them. So basically what I'm saying is, if I have an image and I have text that is related to it, Clip maps the images embedding and the text embedding in such a way that related images and text have similar embeddings and will consequently have a higher dot product. So say I have an image of a dog and I have a text that says a photo of a dog. If I take the dot product between the embedding of a photo of a dog and the image of the dog itself, I will have a higher value than if I took something like plane, car, or bird. So that's what I'm getting. I1.T3 would give me the maximum value. And so I can, in a way, this is letting me know that, I mean, in a way, I'm being able to label my image. If I have a list of labels, if I suppose know that one of these things is there in the image, in this way, I can identify which of these things is there in the image. So this brings us to our problem formulation. So yeah, we are consider a list of visual features F. So I'll again motivate it with an example. Suppose I have a t-shirt and I want to find the list of features for the t-shirt. So I'll restrict my F to only two elements, say color and sleeve. So F1 is color and F2 is sleeve. These are the features of my t-shirt. And now these can be further written as a set of textual classes. So these subclasses for color and sleeves could be, a subclass for color could be black, white, red, blue, any number of colors. So those will be the subclasses represented by T. And the subclass for sleeve could be sleeveless or full sleeved or short sleeved. So those are basically what F and T are. So what I will be trying to do is I will try to label my image with each of these features. So I will try to assign a score as to like how blue my shirt is, how red my shirt is, how sleeveless my shirt is. And in that way, I would be able to label my image in a way. So we now try to perturb the item's image embedding VI with delta such that the item is knocked out of the user's top K recommended list when rescored using the recommender R. So we have our original item embedding obtained using Clip. We just add a perturbation vector delta to it. And we add a perturbation vector in such a way that when I rescore it using the recommender, it is no longer recommended to the user. So this is basically me telling you that you have removed what was actually making this item recommended to the user. And that is why it is no longer being recommended to him. So yeah, and we find this optimal delta using a specialized 3-term loss function and use the non-zero elements of this delta vector to formulate our explanation. So continuing, assume the color example. Assume the 4 colors I had, the 3 colors I had were say black, yellow, and red. And initially black was 0.92, yellow was 0.03, and red was 0.05. After perturbation, after and then rescoring using clip, I got black as 0.42, yellow as 0.49, and red as 0.09. So now red is the dominant color in place of black. So that this will now become a part of my explanation because the argmax over the feature color has changed. So now I will put this in my explanation that if the color had been red, it would not have been recommended to you. So this loss function that we have is a 3-term loss function, which is trying to minimize a collection of things. So first is the perturbation itself. Obviously, I can have a perturbation which makes my image completely black and will obviously be removed from my top K recommended list. I don't want that. Another is I want to remove it from my top K list. So I'm minimizing ReLU of R delta minus RK. And my third is just minimizing the overlap between my initial image and my final image features. Yeah, so this was our example, and my shirt initially had red and sleeve, later it had red and sleeveless. So my explanation will say that if it had been sleeveless, it would not have been recommended to you. We use 3 evaluation metrics. One is fidelity, the other is explanation fidelity, and the third is explanation number. All of these are designed so that we can give a concise explanation that only lists the top features responsible for the recommendation. And as a baseline for this work, we compared it with a random perturbation to the image embeddings and an extension to COUNTIR, which was a method from a few years ago, which didn't directly perturb images, but actually perturbed reviews. So we'll show a comparison of our method with their methods on 2 data sets, which is the Amazon men and Amazon women's data set. So we also performed an ablation study on our losses. We use only L1, L2, only L2, L3, and all of them together, and we show that our method performs better on most metrics. And this is a final slide. It's a qualitative analysis of our explanations. So what we did was we masked an item which the user had previously reviewed and liked. And when that item was re-recommended to the user, we tried to see what our explanation for that was. So this user had given an review. He got it because his favorite color was red. And our explanation says if it had color black instead of red, it would not have been recommended. And the rest of them are similar to that. Right, and that ends it, and I'll open it up for questions.